This is the Grodski solutions to the New York State Regents, June 2012. Let's get started with the multiple choice. As we zoom down, there's 50 of them. Part A, okay, are usually the easier questions, but you decide that for yourselves. Okay, we're starting with atomic structure type of questions in number 1. And here we go. The mass of a proton is approximately equal to the mass of a neutron. Okay, that would be 4. Okay, the nucleons inside the nucleus are protons and neutrons. But if you go to table O, and wow, it magically appears as I say it, okay, we can see that they list the particles here for our viewing pleasures, and notice the top number is the mass number, bottom number is charge, and a neutron has a mass number of 1, a proton has a mass number of 1, they have the same mass. Number 2, an orbital of an atom is defined as the most probable location of an electron. Okay, this orbital is very, very similar to, okay, the orbits that electrons traveled in the Bohr model. Here's the nucleus and here's the planetary model. Because we found that the Bohr model did not truly explain all the properties of all atoms beyond hydrogen, we moved on to the quantum mechanical model, treating electrons as waves, but the regions of space where electrons exist are in these regions called orbitals. So it's a place where electrons exist in the quantum mechanical model. Okay, that's the current model, the quantum mechanical model. Okay. They don't exist in orbits. The reason why we maintained some of the word was to give Bohr a lot of credit in his design because he was the first to quantize the atom, have electrons in distinct energy levels. That's still true today. These energy levels, however, are not in in orbits around a nucleus. They're in regions of space. So to get to one orbital to another, you still need a distinct amount of energy, and Bohr started that, hence why we kept part of the word. Okay, moving on to number 3. What must occur when an electron in an atom returns from a higher energy state to a lower energy state? Well, if you don't remember your Bohr diagram, because he was the first, as I just stated, here's your nucleus to talk about this, electrons existing farther away have to have higher energy, because they're overcoming this positive pulling force of the nucleus. The nuclear charge, the protons, is attracting them. So how can the electrons exist farther away? Well, they need more energy. However, this high energy makes them unstable, which means they're in an excited state, and they're eventually going to be drawn back in with an exact leap, okay? And when they're drawn back in, they release their energy in the form of spectra. So if you didn't know any of that, higher energy state to lower energy state means what? Okay, energy is released, but it has to be specific, because reason why Bohr, okay, was important, he quantized the atom. Quantized means we have distinct energy levels. So you need exactly the amount. That's why the light given off when it emits light, when it jumps back, is distinct in the energy that leaps. So it's very important. That's quantum mechanics. It's about discrete amount of energy. That's why 1 is the answer. Okay. Well, guess what? We're using red, I guess. That's my motif today. All right, even though I can't seem to get it. Okay, moving forward. 4. Which element in the liquid state at 305 in 1 atmosphere? All right, well, couple ways you can look at this, but you have to know the melting points, or at least some of the initial STP conditions of elements. So at STP, it's about 273 Kelvin, which of course is about 0 degrees Celsius. You should know who your gases, who your solids, and who your 2 liquids are. Okay, so magnesium is a solid metal. Okay, gallium is a solid metal. Okay, iodine is a solid nonmetal, and fluorine's a gas. So obviously it's a gas at STP, it's going to be a gas at higher temperatures. So which one of these would melt, okay, at low temperatures? Now if you don't know that, And if you didn't know everything I just talked about here, let's go to the periodic table. And wow, there it is. Okay, so here's a periodic table, and here's what you should know. You should know that this, okay, these guys are gases. I call this the backwards LL rule. So, oh, not that you will. This is a gas, and the Nafkal is a gas. Everybody is a solid except for bromine, okay, and mercury. All right, so that's why I knew fluorine was a gas. However, we need to know of the three solids who has a lower melting point, so we need to go to table S. And there it is again. So let's start with gallium. Gallium has a melting point of 303. Okay, there's a melting point in table S if you're not aware of it. Atomic numbers, symbols, okay, and it has a melting point of 303, which makes it our answer because I believe it was 305. So 305 is over 303. Magnesium, if you want to check, again, for those that didn't see that, gallium right here is 303. So obviously 305 would melt it if the melting point, the temperature is above its melting point. But if you look at magnesium, okay, it's 923. Oh, which one's the melting point? Melting point is right there. 923 is the melting point for magnesium. Iodide, okay, where are you? Next page, I guess. Upside down, great. Okay, where are you? Let me just rotate this. Rotate pages. Okay, so iodide is, its melting point is 387. So that would be the best second place there. All right, so of the three metals, the one with the lowest melting point, and the one under the temperature, is your gallium. All right, and of course that is why your answer is 3. Okay, or I should put answer is 3 here. All right, so next one. Which list of elements consists of a metal, a metalloid, and a nonmetal? Okay, and sorry for that. So I know silicon is a nonmetal. I know carbon is a nonmetal, and I know tin is a metal. But if I did not know that, okay, I can clearly go to my reference table. And boom, there it is. Silicon is on the staircase. There's my nonmetals on the staircase. They separate the nonmetals from the metals. And of course, Ge and Sb are also my metalloids or semimetals. They separate the metals on this side with the nonmetals. So tin is a metal. Silicon is a nonmetal. I'm sorry, I should say a semimetal who has properties of both the nonmetals and metals. And of course, our carbon, okay, is a nonmetal above the staircase. Thus, our answer is 3. Okay, number 6, at STP, which physical property of aluminum remains the same from sample to sample? So, it seems to me that the mass will change. That's called an extensive physical property. Extensive means based on the size of the sample. Extensive physical property. Based on the size of the sample, and mass, length, and volume depend on the size of the sample. Density, we call that an intensive physical property. Intensive physical property, and that of course is independent of the size of the sample. Other intensive physical properties could be melting point, color, okay? Color does not depend on the size of the sample. So density, classic intensive versus extensive property question. Let's move forward. Number 7, and here it is. Which statement describes a chemical property of silicon? Now, a chemical property is one where the ability of the chemical or the piece of matter has to change itself into a new form. So that means a chemical reaction has taken place. You've had a rearrangement of atoms to form a brand new substance. So color is a physical property because you can test for the color, okay, of something without changing its chemical makeup. Okay, silicon being brittle, how hard it is also a physical property. Okay, just to show you that I can spell physical. All right. Silicon melts at this temperature. Melting is just as we talked about, an extensive physical property because it does not, I'm sorry, it's an intensive physical property. And intensive physical properties are ones that you can use to identify the substance. As we talked about previously, number 6, they were looking for an extensive physical property which you cannot use to identify compounds, right? You can't identify aluminum versus gold based on how many grams or how long it is or what volume it has, but you can identify something based on its intensive. So I for identification is how we did it earlier in the year. Okay, if you notice, we're in the area of chemistry. We're talking about chemical and physical properties. We're talking about probably a little bit of chemical organization and classification of matter. Okay, any case, moving forward, like my arrows. 8, which die represents a mixture of 2 different molecules. So now we're talking about mixtures now. So now we're into the part of the course, okay, where we're classifying matter. All right, so a mixture, if you remember, is 2 or more substances not chemically bonded. So they're in close proximity, okay, but they're not bonded. So they're retaining their individual properties because they still are their individual entities. It's when they start bonding they change them. Any case, which die represent a mixture of 2 different molecular forms of the same element. Now, the word element means, okay, same type of atoms. Okay, so same type of atoms. So my friends in chemistry, okay, we're going to denote that with either a dark or a clear, okay, circle for different types of atoms. We know they differ by their protons, all right, the atomic number. All right, so mixture of 2 different molecular forms of the same element. Okay, so molecular forms mean a different arrangement. So here we go. This is a compound, a group with the same type of molecule. So compound, this is. Okay, this is an element. It's a group with the same type of what? Atoms. This could be like O3. This could be HCl. 2 different capital letters, 2 different elements bonded, okay, give you a compound. Same atoms bonded, okay. This is not a mixture. This could be like hydrogens. This is all of the same element, right? It's a mixture, but the same element, okay. This is, again, another example of a compound, 2 or more different atoms bonded chemically. This is an element. So 3 and 4 represent, okay, oops, too big. 3 and 4 represent mixtures of elements and compounds. And this is your answer, number 1, because you have 2 molecular forms. This could be ozone, O3, oops, and this could be oxygen, O2. They're both elements, but they have different molecular organizations or different shapes, and O2 and O3 have different properties because they have different structures. Remember, structure is king. Okay, so back to the question. The mixture of 2 different molecular forms of the same element. So we have to have the same element, but just different structures. That's why 1 is the answer. Okay, 9. A compound is broken down by chemical means during, okay, well, you're breaking a chemical bond, okay. Filtration is a physical change. Distillation is when we boil off 2 or more liquids that have 2 different boiling points, and we know boiling points are physical properties. Anytime you take a phase change, we're talking about physical changes. So we take a liquid and make it go to a gas, its chemical formula is not changing. The distance between molecules are. So distillation utilizes the idea that we're separating liquids based on their boiling point. We did this in our class. We took Coke, okay, and we separated the water by Coke by boiling off the water and then letting it condense into a condensing flask and back into a container. And we separated the mixture of coke based on physical means because mixtures are made and separated physically. Chromatography is when we separated the grape. Remember the grape color was made of purple, so we separated the blue and the red dyes out of grape Kool-Aid because they had different types of solubility. We didn't change any chemical formulas, we just separated a mixture. Kool-Aid is a mixture. Chromatography, distillation, and filtration. Filtration, of course, you're separating large things from small, are all physical separations, how we would separate mixtures. By chemical means, okay, electrolysis is where we needed a battery to create chemical reactions. So that would be your best answer. Okay, let's move on. Number 10, which quantities must be conserved in all chemical reactions? Okay, always the mass. Now mass means that you have the same number, okay, of atoms on both sides. So if we balance how water breaks down when it's under electrolysis, okay, it breaks down to this, we have to balance this. Notice we have 4 H's on this side, 4 hydrogens, and you have 4 hydrogens on this side, 2 oxygens, and two oxygens on this side. So same number of each type of element is what mass means. It's always going to be conserved. Now charge. Now it's hard to see, but this has a 0 charge on this side, and all these are zeros. So total charge is conserved. We see this more in redox, where we have, let's say, copper plus 2, you know, plus another compound, let's say aluminum, and we had aluminum plus 3, and then we have copper 0, and we learned that, hey, you needed what? 3 of these, okay? You needed 2 of these and 3 of these, and we balance. 3 times 2 is plus 6 on this side. This side is 2 times plus 3 is plus 6. We balance the charge as well. And energy is always conserved in chemical reactions, so that's why 2 is the best answer. All right, moving forward. Number 11, which phase describes the distribution of charge and the polarity of the CH4 molecule? Well, the CH4 molecule has, now every time you talk about polarity, you have to separate 2 things. Talk about the bonds and the molecule. You really must separate the 2. And when you do so, you understand that the phrase describes the distribution of charge. If the distribution of charge, which is really the electrons, is even all the way around, we say that there is no one side who has more electrons than another, therefore there's no negative or positive side, and it's nonpolar. It's when we have something like this. Let me draw something. If I have a molecule like that, and there are more electrons on this side than the other side, then clearly this side is going to be a little more negative than this side, and we put the charges there, and that's a polar molecule. Who creates this distribution of electrons? The bonds. And if the bonds are very polar, then electrons are shared unequally. So in any case, these are 4 polar bonds by New York State Regents standards because they're 2 different nonmetals with 2 different electronegativities, so they're sharing unequally. The pair is probably being shared closer to the carbon because it's more electronegative. So there's a polar bond going here. But because of the symmetrical shape, these 4 polar bonds cancel out to be nonpolar. So it's an A. So because of the symmetry, okay, we say that these 4 polar bonds cancel out. Now you can think with me why they would do so. If I have 4 nonpolar bonds and they're equal in all directions all the way around, then there's no difference in electron density. Okay, I always like to say that they're equal in their unequalness. They're sharing unequally in all directions, making a polar bond. But because of the equalness of them being in all directions, that makes every side have the same amount of electron density. Therefore, there's no negative or positive side. Hey, very simple. If it's the same all the way around, it's symmetrical. If it's symmetrical, therefore the polar bonds cancel out. Very simple. Okay, so it's a polar, it has polar bonds, but it's a non-polar molecule because of the symmetry. You know, if you're talking about vectors of the flow of charge, okay, you'd have 4 vectors and 4 arrows coming into each other in equal magnitude. These arrows would cancel themselves out. Another way to look at it. Number 12. What's the charge of the nucleus of an oxygen atom? Okay, it's called a nuclear charge. They're being nice, but sometimes they use this term, nuclear charge. Okay, so some people would say right away, oh, atoms, I hear the word atom, it's electrically neutral. They're talking about the nuclear charge, a charge in the nucleus. So let's go to the periodic table, and there it is. There's our periodic table, and there's our oxygen and all of its glory, and it has atomic number of 8, which means it has 8 protons. And if it's an oxygen atom, all oxygen atoms have 8 protons and 8 electrons if it's an atom. But the atom is neutral. However, in the nucleus, you've got protons and neutrons, and there are 8 protons, so the charge in the nucleus, or the nuclear charge, is +8. So, of course, the answer is +8, but a lot of people would try to throw that 0 because it's an atom, but they're looking at the nucleus. Okay, who has no electrons? Who lost all of its electrons? Well, the answer is hydrogen plus. Now, why? Because hydrogen, its atomic number 1, has a mass number of 1. It rounds off to that most common isotope. What does that mean at the periodic table? It's got 1 proton and 1 electron. So when it becomes H plus and its charge goes up from H0, it lost a negative. So H0, if you remember your redox, goes to H plus. Both sides of a half reaction have to have the same charge. So it lost its electrons. So H plus has no electrons. To break a chemical bond, energy must be what? Always, always absorbed. Now, why is that true? Well, very simply, chemical bonding is a very stable scenario that atoms use each other. Case in point, hydrogen has 1 valence electron. Its configuration is 1. Another hydrogen has another valence electron. Okay? Its configuration is 1. By sharing electrons and using each other's electrons and creating this covalent bond called a nonpolar covalent bond, because they're going to have the same electronegativity and share equally, they now have a configuration of 2. And what does 2 look like? 2 looks like helium. Look, hydrogen has 1 valence. To fill the first energy level, you have to have 2. So if you zoom in and we go find our helium, its configuration is 2. And as we know, the noble gases have the most stable configurations because some of them even have filled energy levels. They have the configurations that are the most stable, the most desired. Okay? So 2 electrons fills the first energy level. That's a stable scenario. So clearly, hydrogen, when it bonds, is becoming stable. And being stable means you have low energy. How do you have low energy? Okay, because you lost it when you're being an atom. So in this case, all right, obviously we have to absorb energy, okay, to break bonds because they're stable. And then when they are freed to make a bond, energy has to be released because you're going into a stable scenario. Here we're stable and we're trying to become an unstable by breaking the bond. It takes energy to break something, if you just remember that. 15, nitrogen atom in the ground state. Well, in the ground state, that just means electrons are filling their lowest energy orbitals, or I should say shells first, how we want to talk about that. So let's go back to the periodic. Okay, so here we are with nitrogen. And nitrogen has a configuration of 2-5, has 2 electrons, okay, in the first energy level that fills, and then has 5 more. So when we show Lewis dot diagrams, we show the electrons that are available for bonding. These 2 electrons are filled. The first energy level is filled. Guess what? Just like we just talked about with helium, this is stable. These electrons are not stable because we would need to have 3 more electrons, okay, to become like the noble gas counterpart. So it likes to become -3 by gaining 3, and then it'll be stable. So when we draw the dots represent valence electrons, and they'd be 5. Some people like to use the top of the row. 15, take the 1 away, 5 dots, 5 valence. So I'm going to put out the electrons available for bonding. And that, of course, would be 5. And here's our 5 dots. That famous lone pair that makes it a nice base. All right. 16, what is the most likely electronegativity value for a metallic element? Metals notoriously are large atoms. Therefore, their electrons are farther away from the nucleus than other atoms, especially let's say, nonmetals who hold on to electrons more tightly. So they tend to have less attraction. Electronegativity is attraction for electrons, so they have less attraction. So I'm looking at my numbers. I could go to table S and see which one matches an element, and then find that element to see if it's a metal or not. But I can see that the best answer for me is the lowest value. Less attraction, that's why they are big, that's why they tend to lose electrons, that's why metals tend to, remember, oxidize. See, we're putting together all our units. They lose electrons. That's why iron rusts. It becomes iron plus 3. It loses the electrons, okay? The corrosion of metals. The metals lose the electrons. Okay, 17. Which polyatomic ion has a charge of -3? Well, we have a table called Table E. I call it the what the heck is that table because you see these things and say, what the heck is that? So we're going to go to Table E. And here is Table E. And chromate is -2. Oxalate, where's our oxalate? -2. Whoa. Okay. Another table wanted some time on the telly. Okay, so we have chromate, we have oxalate and thiocyanate. This thiocyanate's -1, okay, and oxalate's -2, chromate's -2, and of course, just looking up phosphate, -3, and there's your winner. So the phosphate ion. Okay, well, what the heck is that table? Yeah. All right. So let's go on to 18. All right, so number 18, every chlorine atom has how many electrons? Now, they said the word atom. Atom is neutral. Okay, so chlorine, the proton number equals the electron number. Okay, so if you're going to be neutral, electrons have to, which are -1, equal the protons, who are +1. So we go to our periodic table, and we find our chlorine in the group 17 family called the halogens, and its atomic number is 17, which means it has a nuclear charge of +17, and of course that means it must have 17 electrons to make it an atom. Atom means neutral. So therefore, every chlorine atom has an atomic number of 17. They could have said 17 electrons as well. All right, the atomic number, the proton number, identifies the element. 19, which substance cannot be broken down by a chemical change? If it cannot be broken down chemically, and that means you're breaking bonds, right? A chemical change means you're breaking the bonds between the atoms. So that means that you either have no bonds or you're just atoms. Ammonia, you should know already from your entire year of chemistry, is NH3. Methanol, you should know from your organic chemistry unit, is a 1 carbon with an OH group with the H's that can be broken down. So can ammonia because they have different atoms chemically bonded. Propane from organic chemistry is 3 carbons, single bonded. Fill in the rest with H's. These are bonded with hydrogens. Okay? And phosphorus, there's an element. That's element P, so just made up of 1 atom. So if you didn't know that phosphorus is an element, you look on table S. But these, you should be able to know that these are compounds. And compounds are broken chemically because you have to actually break the bond between the atoms. Okay? And that's what a chemical change is. Breaking bonds and forming new ones. Here, they're just the same type of atoms. Number 20. Standard pressure, which substance becomes less soluble? Solubility is the measure of how well a substance will dissolve in water or be affected by the solvent as temperature increases. All right, now we know that solubility, how well a solid substance, breaks into particles and can be surrounded by water, is based on if it's a solid, temperature. So as temperature increases, we should be able to dissolve more. But this question is saying, which substance becomes less soluble in water as temperature increases? We know that solids solubility increase as temperature increases, and we should know that gases decrease because gases already have weak attractive forces. If you give them more energy as temperature increases, they'll have even more energy to overcome these weak attractive forces and go into and leave the solution. So let's go to a table that kind of reminds us of this. Okay, this is table G, solubility curves, and you notice as temperature increases, most of our curves go up, okay? If you notice, there's a few of them where the curves are going down as temperature increases, and look at this, it's ammonia, sulfur dioxide, hydrochloric acid, or hydrogen chloride. These ones that are going down as temperature increases are the gases. So gases solubility decreases, temperature increases, and we call it thermal pollution. As you add more heat to a small body of water or a large body of water, you lose your dissolved gases. Okay, but most of these are going up, and the ones that are going up, okay, as temperature are solids. And that's something you should know. Solubility of a solid increases as temperature increases, solubility of a gas decreases. And this table G reminds us of that. So of the four choices, our answer is going to be hydrochloric acid because it's one of those three curves. It's going down. Hydrochloric acid was an ammonia, and sulfur dioxide from table G were going down. They're the gases. So that's the one of the three there. These guys are all solids. They're going up on that table. 21. Which type of concentration is calculated, okay, when grams of solute is divided by the grams of solution, and the result is multiplied by 1,000,000. Okay, well, if you're not sure, we have a reference table called Table T that shows us our formulas for different solutions. Let's go to that now. Okay, here is Table T, and we're going to zoom in here, and we're going to look for, okay, our concentration formulas, and see what we have here. And let's see, concentration, let's see, mass of site over the mass of site times 1,000,000. That 1,000,000 kind of sticks out, and there it is, part per million. There's your molarity. So it's really, then you identify parts per million. There it is. And there it is, number 2, parts per million. Number 22, which type of energy associated with random motion of molecules? Motion of molecules, I'm thinking temperature. Okay, and temperature is motion, and thermal, okay, is a word that describes heat. Heat is basically the motion of molecules. So higher temperatures, you have more heat. Thermal, so thermal energy is a word that describes the energy of motion or heat. Chemical energy is the energy in bonds that are released, okay, when you form new ones, or absorbed when you break old ones. Electrical energy, energy from a battery or voltaic cell. Nuclear energy from splitting the atom in fission or fusing the atom together, okay, of light nuclei in nuclear fusion. Okay, but the best one about motion, you should know that heat is tied to temperature, which is tied to the motion of molecules, choice 4. All right, moving forward. Number 23, the temperature of a sample of matter is the measure of, and again, a very similar question. They go hand in hand to each other, how they go in order of these tests. So temperature is motion of particles. Kinetic is a fancy word for motion. So temperature is a sample of matter is the measure of the total energy. No, we don't measure thermometer. We don't use thermometers to measure total energy. Total potential energy, a thermometer doesn't measure the potential. Okay, it just measures the average motion. Average kinetic energy is what a thermometer measures. It's a definition of temperature. Temperature is average kinetic. Potential energy a thermometer cannot measure. Okay, and a thermometer doesn't measure all of the energy, just an average. Okay, for those that had me in class or your teacher, maybe they showed you a distribution graph of different speeds of different molecules. And we use that average speed or the average temperature. As temperature increases, these things actually flatten out, and your average, which is in the middle here somewhere, increases, but it reflects particles that have what? High speeds and particles that have low, and we take the average. So temperature is the measure of the average kinetic energy. Just that simple. Okay, 24. Which unit is used to express the pressure of a gas? Okay, well, if you remembered anything from your class, you know that mole is a how many number, joule is used for heat, Kelvin is temperature, so that leaves Pascal. But if you remember, you've been talking at one of your units of pressure, you know that at STP, we know that it's at 273 standard temperature, Kelvin, and we know that's also 101.3 kilopascals. So Pascal is a pressure unit. But if you still did not know that, there's a table that's often forgotten about. Let's go there. Okay, there's a selected units table. Okay, and it gives you the type of quantity that a certain unit measures, and guess what? Pascal is pressure. So if you didn't know that, there's a little place there of units. Okay, so mole is amount of substance, joule is heat, all basically a straight reference table question. Okay, number 25. Which sample of matter sublimes at room temperature at standard pressure? This is something that you should have experienced in your chemistry class, and there are two basic ones. Iodine, okay, iodine, I2, naturally sublimes from a solid to iodine gas. All right, sublimation is from a solid to a gas. Another example is dry ice. Carbon dioxide, okay, is called dry ice because it skips the liquid phase. It goes from a solid directly to a gas, just like iodine. Those are the two you have to know. And sublimation, again, is from gas to a liquid. And the reason why we skip the solid phase on the New York State Regents level is because of very, very weak attractive forces. CO2, if you remember, is nonpolar, so it exhibits those weak forces that we use, which are really London dispersion forces. And those weak forces are not enough to keep that in the solid phase. In truth, CO2 sublimes because it's triple point, okay, and where the current temperature is, but we'll leave that for another course. This is New York State review. Number 26. All right, so we're going to move down here. Number 26, given the diagram representing a closed system at constant temperature, every time I see these closed systems, I'm thinking, okay, we're talking equilibrium. The rate of evaporation is equal to the rate of condensation, because we know that a closed container, this line is not going to change. We know at equilibrium the amount of gas and liquid is going to remain the same. All right. In any case, I don't know what the question reads, but that's what I think right away. Which statement describes a system in equilibrium? Well, equilibrium means that things stay constant because their rate of the forward equals the rate of the reverse. So the mass of the H2O liquid equals the mass of the gas. Probably not the case since gases have low density. It's not about the masses equaling, it's about the rates being equaling. The volume, no. The moles, no. The rate of evaporation, as I said before, equals the rate of condensation. It's about how fast. The forward reactions rate, okay, equaling the reverse reactions rate, okay, and that means if two people are on this line and we have 4 people on this line, I make people switch lines, one person per every minute, there'll always be 2 people at this line. They're going to change their positions, and there'll always be 4 people at this line, but okay, the amount of people on these lines stay constant because we're switching lines evenly. Okay, so that's why that is a 4. All right, so let's go back up to the top. And number 27, which reaction occurs at the cathode in electrochemical cell? Now, electrochemical cell that could either mean a voltaic cell, which you guys should know, voltaic, which is the battery, or electrolytic cell that requires a battery. Okay, so it could be anything, and we know that this mnemonic you probably learned in your class, anox, red cat, occurs for both types of cells, whether you are producing the volts or you need the volts. So red cat means we're talking about reduction. Okay, And reduction, okay, is what occurs at the cathode. Red cat, choice 4. Combustion is oxygen plus what? Some carbon-based fuel to make CO2 and water. The top of table I does that. Neutralization is an acid and a base makes salt and water. And oxidation would occur on the anox, the anode of electrochemical cell. Okay, and it does not matter whether it's voltaic or electrolytic. Okay, anox red cat works for both. Nice little redox question there. 28. Which substance yields H pluses? This is acid and base territory as the only positive ion in an aqueous solution. This is the old Arrhenius definition. So looking for an Arrhenius acid. Okay, well, look at organic chemistry. This Cho Mama group, this is an aldehyde. This is an alcohol, right? This is an R with an OH. It's an R with a CHO. This is a Cu group. That's an organic acid. And as I keep telling you people, they love to pick on the organic acids. And of course, acids give off protons. So of course, that's the answer. Okay, and I'm using table R here if I didn't know what these are. But the Cu group is famous for the acid. This is on either side of the carbon is an ether. And I'm only using my knowledge based on table R. Okay, so that's an organic acid. Besides, table, I believe, K gives that as well. Let's take a look at those reference tables. So there is table K, all the common acids you probably will see. Okay, and there it is, the Cu group, ethanoic acid. All right, it's vinegar. Okay, acetic acid, H in front. This is the structural formula. This is the molecular formula. Okay, it's an organic compound. Let's go to table R. Okay, table R lists the functional group. There's the alcohol. R is the rest of an organic compound. It's not a base. Ether is on either side of a single bonded oxygen. Aldehyde is at CHO at the end. Okay, and the organic acid has its COOH at the end. And that's how you know that was the acid. And acids, of course, are electrolytes. They love to pick on the acids. So, of course, the organic acid is the answer. All right, moving forward. Number 29, compared to the mass of the penetrating power of an alpha particle, the beta particle has it's going to have a greater penetrating power. And the reason is, a beta particle, which is from your nuclear chemistry part of your course, is a lighter particle. It's essentially an electron. It has a mass, they put a 0 for its mass, but it's 2,000 times lighter than a proton or a neutron, and has a charge of -1. And I'm getting this notation from table O, or as we say in Brooklyn, table O. Okay, so table O, let's go there. Now, table O lists all the symbols used in nuclear chemistry as it reads. Good reader I am. But it gives you the particles that are usually emitted from the nucleus for them to get stable. The alpha particle, you should already know, is a helium nucleus, a mass of 4, 2 protons, 2 neutrons. A beta particle is essentially an electron. They put a 0 here to show you that its mass is really insignificant compared to the mass of a proton or neutron. By the way, a proton has a mass of 1 and a charge of +1. The top number is, of course, the mass number, bottom number is charge. Gamma radiation has no mass and no charge, and an alpha particle is really heavy compared to these. Now, penetrating power is really about, it's about the mass. Those that are massive move slower and have a tougher time penetrating. So alpha particles have the least penetrating power because they're the heaviest. They move the slowest. Okay, beta particles, wow, that's pretty penetrating because they have very little mass compared to an alpha particle. I mean, wow, it's a big difference. If an electron, which what a beta particle is about 2,000 times lighter than a neutron, then my gosh, this is a really small particle. So beta particles have a great penetrating power than alpha particles. That's why beta decay or radiation is very dangerous. Gamma radiation is even more dangerous because gamma radiation has absolutely no mass and no charge. And I may say, what does a charge have to do with anything? Well, if you're an alpha particle, okay, you have a +2 charge, which means you're going to be deflected toward negatives. If you're negative, you're going to be deflected toward positives. Well, these guys don't get deflected by electromagnetic fields because they have no charge, and they themselves are electromagnetic radiation with very high frequencies, very high energy. So the one that's the lightest, absolutely no mass, okay, would be the gamma. Let's go back to the question though. So from going from table O, we notice the alpha particle being a helium nucleus with a 4/2 being much heavier than the alpha particle. We know that 0 is not true, but it is very light compared to that. Okay, beta particles have less mass, therefore can move faster, okay, and are able to penetrate with their energy better than something that's more massive and slower. So number 1 is the best answer. Now, if of course they had gamma particles here, that would be the winner overall. That's why gamma radiation is the most dangerous of all. Okay, number 30. During a nuclear reaction, this is important you understand the difference. Nuclear reactions are not reactions of electrons. They're reactions of the nucleus. Carbon-14 spontaneously will decay by giving off a beta particle and making nitrogen-14. Okay, this nuclear equation that you wrote in your class is showing how the nucleus changes. Okay, any case, mass is converted into energy in nuclear reactions. Okay, isomers, these make no sense. Okay, these are all about, this is about electrons, isomers, a structure. We're talking about the nucleus. And when you have a nuclear reaction, you mass all of the particles on one side and mass all the particles on the other. There actually is a little bit of missing mass involved in every nuclear reaction. Not much here, but in fission and fusion, a lot more missing mass based on Einstein's E equals mc change of E equals mc speed of light squared. And if this is a huge number, speed of light, square it even bigger and times it by a little mass missing, you get tremendous energy in fission and fusion. Okay. Now we're going to move on to something called Part B1. These are multiple choice questions. These are supposed to be a little more challenging and of more difficulty. Some of these are supposedly two-step. Sometimes I see that, sometimes I don't. Notice the questions we just went through kind of paralleled the course. Notice we ended up in nuclear chemistry. There was what? There was some equilibrium, some acid and base, some electrochemistry, okay, and now you had some acid and base, and now we had, okay, some nuclear chemistry. So it kind of goes in order, interesting enough. So you know what questions you get wrong, what you need to work on. So number 31, the atom of a ground state has 2 electrons in the first shell and 6 electrons in the second shell. What's the total number of protons in the nucleus of this atom? Well, once you tell me protons, I want to find the element. They said it has, the ground state means electrons are filling, okay, in order from lowest energy to high energy. They didn't say an ion, okay, they said atom. So the key words here are ground state, key words here are atom. So if I know the configuration or I know how many electrons we have, I can find the number of protons. Because when you have an atom, as we talked about, protons equal electrons. They're neutral. Atoms are neutral. Has to be. So 2 electrons in the first shell and 6 electrons. So you can take this configuration and you can go match it with the periodic table, or you can just add these 2 numbers and that's 6 protons. Okay? So the number of protons would have to be, not 6, I'm sorry, 8. 6 plus 2 is 8. Check out my math. All right? So save myself there. So 8 protons is the answer. Don't know how that's a tough question, but again, if you didn't know that, okay, protons equal electrons. And again, you could look up 2-6 on the periodic table. And here is the periodic table. And let's zoom in and let's go find 2-6. It's oxygen. And of course, oxygen has 8 what? Protons. And of course, 2-6 equals 8. Of course, it's an atom. Number 32. A bromide atom in an excited state could have an electron configuration of what? All right, so key here is excited state. That is a clue here. And of course, an excited state is the idea that electrons as we've talked about already in this test, this is the nucleus that's positive, and here's the different electron shells based on mostly proximity. Electrons farther away have higher energy. In any case, if I have electrons that are in the ground state, that means they are in the lowest level possible, okay? And if energy is coming into the atom, these electrons, if the energy is discrete enough, is it a certain number, it will actually be able to leap to higher energy states and be excited. It's not going to stay there very long, and it's going to jump back, and when it jumps back, it gives off the extra energy it has in the form of light. But we're looking for a configuration where an electron, okay, is supposed to be. We're looking for a place that's missing an electron because it jumped. So let's look at these configurations and which ones are going out of order. Now they said it's a bromine atom. That is a clue. Okay? Now atoms, if I've already said, mean that they're neutral. If they're neutral, that means they have the same number of electrons as protons. Let's go find a bromine atom from the periodic table. Okay, so here's our periodic table. And we're going to go find bromine, which, if you don't already know, is a halogen. It's in group 17 in that same family. And there it is. And look at its electron configuration, 2-8, 18, 7. So it's got 7 electrons, okay, beyond the third principal energy level, right? This 2 means 2 fills the first. 8 fills the second, 18 is filling the third, and now we have 7 beyond the third energy level. So these electrons are stable. These are valence. Now, this is a ground state configuration. This is the electrons filling in order. Okay, all atoms are listed as atoms, which means their electrons equal their protons. So we should have 35 electrons listed here. And if you count, 8 plus 2 is 10, 10 plus 18, okay, 28 plus 7 is 35. So when you're in excited state, doesn't mean you become an ion. It means that you still have 35 what? Okay, electrons that equal your protons, but they have to be going out of order. Like this could be 2-7, 18, 8. It could be 1-8, 18, 8. Okay, notice I can't have more than the max total. Okay, so let's look for something with 35 electrons that is going out of order, missing electrons that have leapt, or leaped, I should say, to higher energy states. Okay, so we know that 2-18-7 is the ground state from the periodic table. So this is not the answer. This is the ground state configuration. Okay, and number 1 is going in order just like number 2, but has 1 less. So this is the element. If you go to your periodic table, all right, selenium, exactly in order. So not what we want here. Okay, so let's go on to choice 3. Okay, choice 3 is 2-8-17-7. Okay, looks like we're missing an electron here, but shouldn't that have jumped at least to the 4th? If it's going to be 2-18-17, and that should be an 8 here, right? Because if I'm going to miss electron. So this, okay, is actually the excited state configuration, this one, of selenium, right? Not of bromide. This is going out of order. So this is excited state, no doubt about it. This is an excited state configuration, number 3, but of the wrong element. This has 34 electrons. So the answer and the winner, okay, is choice 4. It has, if you count, 8 plus 2 is 10, 10 plus 17 is 27, 27 plus 8 is 35. So this is 35 electrons, and if you can see, it's jumping out of order. An electron in the third energy level jumped to the 4th. That's why this number goes up. Okay, so choice 4 is the answer. 33. Atomic masses and natural abundances of the 2 natural occurring isotopes of lithium are shown in the table below. Okay, all right, so we have lithium 7. Now, some people hate this idea, but if you look at lithium, it's -6. What does that mean? That means that Lithium has a mass of 6. And why do they do that? Well, because almost every single element, okay, of course the natural occurring ones, have multiple masses that they can have for the same atom. These are isotopes. Iso means same. Same element, same number of protons. By the way, lithium's atomic number 3, so they both have 3 protons. They're both atoms. Don't confuse isotopes with ions, so they all have 3 electrons. The only thing that differs is their neutron number. So 6 minus 3, this has, okay, 6 minus 3, this has 4 neutrons. Remember, we do that. Lithium is 3. This number they're giving me is the mass number, and that's, of course, 3, if I can do my math, which I apparently cannot. So 6 minus 3 is, this is 3 neutrons. 7 minus 3 is 4 neutrons. So I'm giving you the element lithium with 3 protons and 3 neutrons. That's lithium 6. And there is lithium with 3 protons. That makes it lithium with 4 neutrons. Okay. They exist in nature with different abundances. Okay. All right, here we go. Which numerical setup can be used to determine the atomic mass of lithium? This is the weighted average problem. Okay. So how we go about doing that is very simple. We're going to take a weighted mass, or weighted average, I should say, between these two. And all you do is this. We're going to take 7.5% of 6. Now, we take a percentage. Remember, you move the decimal place 2 places. So you take 0.0075, and we're going to times that, 0.075, moving it 2 places. Okay, so 0.075, and we're going to times that by 6.02. That's its mass. And then we're going to add that result when we find 92.5% of 7.02. Okay, so to find 92.5% of anything, you move the decimal place 2 places. I'll get this correct, I promise. 0.925. And I'm going to times this by 7.02. And I add that result together. Okay, now it seems very foreign that we're doing this, but you know, if we did a straight average, you know, real quickly, if you do a straight average, like if I have the average between 14 and 12, everyone knows that the average between 14 and 12 is a number in between, which is 13. How do I do that? Well, if I'm going to do a straight average like I've been doing in all my math classes for the rest of my life, because usually weighted problems like this are something you only see in chemistry, but, okay, we know the answer should be 13. So if 50% weighting is 14 and 50% weighting, okay, is 12, watch how we do this. We've been doing this all along, or you have, okay? So here's what we're going to do. 50% of 14 is what? 7. 50% of 12 is what? 6. Add them together, you get 13. So when you average, you've been doing this, you've been giving these values equal weights. We're just now changing the weights because in nature, okay, the relative abundances of occurrence of these different isotopes, lithium 6 and lithium 7, occur not at equal percentages. This one's more heavily weighted. Lithium 7 exists in much higher quantities. That's why this one rounds off to 7. So obviously the answer to our problem is 0.075 times 6.02 times 0.95, 0.702, choice 1. Okay, 34. Element X reacts with chlorine to form an ionic compound. That's your hint. Ionic compound. Ionic compounds, okay, are compounds that make ions, and these ions are attracted to each other to form that compound. Now here's the formula they give me, XCl2. All right, XCl2. Now, they want to know which group, which is a column on the periodic table, could X belong to. Well, I'm going to do a little bit of my assigning oxidation number skill that we learned in Redox. I know that chlorine, if it's going to be at the end, and I'm dealing with something in front who has to be positive, right? Ionic compounds, the front one's positive, the end one is negative. If it's ionic, I know it's making these ions. So let's go find. So X has to be positive, chlorine has to be negative. If you don't know what charge halogens are when they're negative, we go to the periodic table. And there it is. So chlorine, my gosh, can all be these different choices. So what do I pick for chlorine? Well, if chlorine's in an ionic compound, all right, and it's bonded with something positive, well, guess what? It has to be negative. Being that chlorine was at the end of that molecule, it has to be negative and only has one negative choice. So therefore, that's our starting point. So chlorine's -1. There's two of them, -2 overall. This thing has to equal 0. So this has to be +2 overall. Since there's only one of this compound, it's +2 individually. So we are looking for this X, or this compound, that has to be +2. And you should know group 2 elements become +2. If you don't know, let's go to the periodic table. And there it is. Group 2 elements all become +2. Look very carefully. They have 2 valence electrons outside of their filled valence shell. Core electrons. Okay, so there's 2. So they like to lose 2 electrons to become as stable as their noble gas counterpart. Like beryllium likes to lose 2 to become just 2, which is helium. Magnesium likes to lose 2 to become 2-8. 2-8, if you want to embark on a little journey here, is neon. So that's how that works. So obviously all group 2 atoms are +2. Moving on to number 35. So 35. 35, here we go. Which general trend is found in period 3 as the elements are considered in order of increasing atomic number? The general trend, the reason why they say general trend is because sometimes there are a few exceptions that buck the trend, but generally speaking, in period 3, you should know, is the row 3 in the periodic table. So if you're talking about a row, we're going across, not down. Those are groups. Elements are considered in order of increasing atomic number. So that means that we're going from left to right on the periodic table. All right, and you can look at that yourself on the periodic table. Now, what's happening? What's the general trend? There's increasing atomic radius. Okay, well, we should know as we go across the periodic table, the radius gets smaller because we're becoming more like nonmetals. Metals hold on to electrons loosely. Nonmetals, okay, hold on electrons tightly. Now, as you go across the periodic table, you should know that the nuclear charge, the charge in the nucleus, gets more positive. There are more protons inside the nucleus of atoms off to the right, so they pull in those electrons in tighter, so their radius is smaller. Nonmetals are toward the right, so increasing atomic radius makes no sense. Increasing electronegativity, that is going to be our winner, because electronegativity is a fancy word for attraction for electrons. Attractions. And these attractions are much higher for nonmetals who are off to the right, up in the right in the periodic table, because they have the greatest amount of protons, okay, at least in their row. Okay, if you look at fluorine atomic number 9. Look at lithium, atomic number 3. These are in the second row. Fluorine has 3 times the number of protons as lithium, so therefore it is going to be much, much smaller because it pulls in and attracts the electrons a heck of a lot more, and the electronegativity is so much higher. The atomic mass, of course, increases as you go across, and the amount of energy it takes to pull an electron away from a smaller atom is much higher for smaller atoms. First ionization energy is the energy it takes to pull electrons away. Well, if you're pulling them in tightly because you're a small radii, you need a high energy. It increases. And by the way, you could look at these at Table S. Table S lists these two values, and you can look at those trends, and you have that kind of time. Choice 2 is your answer. Number 36. Which molecular formula and empirical form represents this compound? Okay, well, empirical formula is the lowest ratio, and the molecular is the formula it exactly exists in nature. Okay, so let's count to find the exact formula. We have 1, 2, 3, 4 carbons, so C4. Well, let's do H's. 1, 2, that's H2. Let's do oxygens. 1, 2, 3, 4. So we have 4 O's, and then we have 2 N's. So this is the actual number of atoms that exist in this molecule, so we call this the molecular formula. Okay, now the empirical is the lowest ratio, so let's reduce this. Okay, well, that would go from this to C2H02N. That's the lowest whole number ratio. That's the empirical. All I did was divide everything by 2 because they could be split in half. I just went the lowest ratio. Okay, so look at our choices. Which molecular formula, okay, represent this compound? So that they said molecular first. So if you counted with me, it's C4H2O4N2. Okay, and there it is. There's your molecular formula, the one we got. Now, of course, the N and the O is switched. It doesn't matter. And then the lowest ratio, by finding the lowest whole number, dividing everything by half in this instance, because we wanted at least to have come down to 1H, we have C2H02N, and this is not the correct empirical. This is the same molecular, and this is the empirical that we get above, so choice 4. Actual formula, lowest ratio. Number 37. What's the gram formula mass of ammonium phosphate? This is an ionic compound, okay? It's the ammonium ion from table E that sometimes I call the what the heck is that table. Any case, let's figure this out. The gram formula mass, and this I think our first real math question here. All right, so gram formula mass is the mass of 1 mole. So we're going to have to add up all the atomic masses here. So we have 3 N's, 3 times this. So this is 3 N's. So we have 3 N's. 3 times the atomic mass of N is 14. Now again, if you didn't know that, I'm getting that from the periodic table. All right. So we're going to need atomic mass of N, hydrogen, phosphorus, and oxygen. If you don't know those, we go to the periodic table now. So we needed the atomic mass of oxygen, which is 15.994, which is going to round off to 16. That'll give us the most abundant isotope, O16. We're going to have nitrogen 14. We'll round that off too. We have phosphorus 30. Okay. And we're going to need hydrogen. I'm sorry, phosphorus will be 31 when we round it off. And hydrogen will be 1. And those are the values we need to come up with the grams per 1 mole of that compound. So I'll start again. We know that N is 14 atomic mass. We know that H is 1. We know that phosphorus is 31. And oxygen is 16. Okay? So we have to find out how many of these. So if I have 1 mole of this compound, I have 3 moles of N. So 3 N's. 3 times 14, okay, equals 42. Then we have how many H's? We have 3 times 4, right? Per one of these is 4, but there's 3 in the parentheses, so we have 12 hydrogens. So we take 12 times the atomic mass of hydrogen, which is 1, and that gives us 12. Okay, then we have 1 phosphorus, 1 times, there's only 1 there, okay, 31, which is 31, and then we have 4 oxygens. Each oxygen is 16 from the periodic table, so 4 times 16, okay, 64, and now we're going to add them together. When we add these together, we get 149. And that's grams for every mole. And lo and behold, that's choice 3. Number 38, in the ground state. Now, they're telling you that because they don't want you to confuse excited state, electrons jumping farther away from the nucleus. Which atom has a completely filled valence electron shell? That means it really has no valence electrons because that shell, or that principal energy level that electrons are filling, are filled. And you should know your noble gases have filled valence shells for the most part. Okay? So if you look at your periodic table, helium and neon fill their entire shell. Helium holds 2 electrons. 2 electrons are the electrons in the first energy level. That's the maximum, so they fill that. Neon have 8. Okay, so these two especially, they fill their entire principal energy level, that shell, and that's what makes them so stable. They don't need any more electrons or want to lose any electrons. They have that stable configuration. That's why neon's the answer. Choice 3. Okay, number 39. Given this formula, the bond between two atoms, which two atoms has the greatest degree of polarity? Okay, polarity means that we have the greatest difference in electronegativity, which means we're sharing electrons the most unevenly. Okay, so if you look at between carbon and carbon, they are the same atoms, so their electrons, this dash really represents an electron pair. So they're sharing electrons evenly. Therefore, either side of the bond doesn't have more or less electrons. They feel the same amount of electrons between them, so there's no difference, there's no poles. To be polar means you're going to have major differences across the bond because you're sharing electrons really unevenly. Now, carbon to hydrogen, there's a slight difference in electronegativity. Carbon's a little more electronegative, so carbon's going to feel them a little more, a little closer. So there's some polarity there according to New York State. Okay, now the carbon to oxygen, okay, all right, is going to have a good deal of polarity here, and so does oxygen to hydrogen because it has a high level of electronegativity. So to get the correct answer, let's go look at Table S. And Table S is going to give me electronegativity values. And that's going to tell me who's sharing electrons, okay, more or less, so we don't make any incorrect guesses. So we need oxygens, carbon, and hydrogen's electronegativity. Let's go to Table S. Okay, hydrogen's electronegativity, its ability to attract electrons through a bond, is 2.2. Carbon is 2.6. That's why before I showed carbon kind of pulling on that pair more. Then we have our nitrogen 3.0, but we don't have nitrogen in our problem. We have oxygen, which is, in this case, 3.4. Okay, so 3.4 is the electronegativity of the oxygen. Okay, 2.6 is the carbon, and 2.2 is the hydrogen. So the carbon is 2.6, hydrogen is 2.2, and the oxygen electronegativity is 3.4. Okay, this tells me what kind of strength each atom has for a pair of electrons. So, as you notice, carbon being 2.6 and hydrogen being 2.2, carbon pulls this pair closer, slightly polar. These are, of course, the same. Carbon 2.6, oxygen is 3.4. So between this bond, oxygen pulls that pair closer, and this side feels electrons more. The difference is oxygen is 3.4. Carbon is 2.6, and the difference in electronegativity between 3.4 and 2.6, if you subtract, okay, is going to be 8. So if you don't believe me, 3.4 minus 2.6, okay, is going to give me 8. 1 point, I should say. Oh, I'm sorry, just 0.8. Okay, so that's the difference. That means that oxygen is going to create a more polar bond. Now, hydrogen has a 2.2. Okay, so we got to figure out if the difference in electronegativity is greater between carbon and oxygen or oxygen and hydrogen. Okay, let's get rid of this right here. And that's where this question is coming from. And what we're going to do is 3.4 minus 2.2, and you probably could see already that this is going to be a greater difference in electronegativity. So the greater the difference, 1.2 here or the 0.8 here, okay, clearly they're sharing electrons even more unevenly between these two because the difference of their strength for attracting electrons is much greater. So this pair is even shared even more unequally, creating a more disparity of charges or polarity. This is like almost +1, almost negative. So the O to the H bond, okay, has the greater difference in electronegativity. Choice 4. Okay, so we have our heating curve for question number 40. Okay, this heating curve, hey, I know this is going to be my solid, my liquid, and my gas. I know this is solid going to a liquid. I know this is a liquid going to a gas. If I wanted the temperature of this phase change, I could look at the place where it stays constant. Let's go see what kind of questions they have. During which time interval is the average kinetic energy of the particles of the substance constant? Constant. Okay, well, average kinetic energy, my friends, in chemistry is temperature. So the temperature is remaining constant right here at the phase changes. Okay? Now, they said while the potential energy of the particles increases. Now, potential energy is not measured by a thermometer. A thermometer measures temperature. Temperature is the average kinetic energy. So this is kinetic energy. Okay? Okay, this does not measure potential. But we do know this. As you add energy, this is an endothermic graph. You're adding energy. A solid is going to a liquid, going to a crazy gas. Energy is going up. You have to add energy to make this happen. So this is endothermic. And anytime you add energy to a system, the potential goes up. Think about giving energy or sugar to a young child. The potential for them, okay, to act a little more crazier increases. So as we give energy, the potential increases on every segment of this line. Don't fall in love with thinking potential follows this line. If you give energy to something, follow, as I tell my students, follow the what? The general curve. The curve is generally going up, so therefore, over every segment, potential energy is going up. Obviously, potential energy is going down as you release energy through every segment. Okay, so we want to go left to right, and we want to find either B to C, and I see that there, or I want to find, okay, D to E, but not the other way around. So that's why 2 is the answer. 2 is we're adding energy, so our potential is going up, and we're picking an interval where the temperature or average kinetic energy is staying the same. B to C, choice 2. 41. Okay, at 50 degrees Celsius and standard pressure, the intermolecular forces of attraction are strongest in a sample of what? Well, looking at these 4 compounds, you may say, well, how do I know? Okay, well, you know ethanoic acid, you know ethanol, propanone. You should be able to know what these chemical formulas look like, but still you may not know anything about their intermolecular forces of attraction. Or, given this very specific piece of information, you should know that you need to go somewhere to look. And that place to look is a table, and that is a table of vapor pressures, right? So let's go there. And wow, there it is. Okay, so it's table H. Okay, it's the vapor pressure. Now, vapor pressure is a fancy word for, I think, the rate of evaporation, right? So vapor pressure is gas, and it's gas pressure due to the liquid molecules escaping into the gas phase. So you have these 4 liquids. Who's going to evaporate the fastest? Well, propanone is. So they said at 50 degrees Celsius, so let's choose a temperature, and here it is. Okay, it's my poor attempt at a straight line. Okay, and here it is right here. So at 50 degrees Celsius, at this temperature, who is evaporating the best? Propanone is. Okay, it's producing the greatest amount of pressure due to molecules escaping because a lot more of its molecules are escaping. Ethanoic acid has the lowest. It's resisting evaporation. Now the question read, let's go back to the question. They wanted to know who had the strongest intermolecular attractions. So who is attracting the molecules of each other the strongest? Now, if you're attracting your own molecules stronger, it's harder for you guys to get away from that and evaporate. So of the 4 elements, which one is resisting evaporation? Who has the lowest vapor pressure, right? The vapor pressure would be lower because you are holding on to each other stronger. So if you're holding on to each other, these force of attractions are greater, you're going to have less evaporating molecules escaping from each other. So of the four, ethanoic acid from that table had the lowest vapor pressure. Okay, and that's why 1 is the answer. And again, if you want take a look back on table H, let's do. So we can see that the lowest line here at 50 degrees Celsius is the ethanoic acid. It has the strongest intermolecular attractions because it's resisting evaporation. Number 42. At this pressure and this temperature, what's the total amount of heat released when 1 mole of aluminum oxide is formed from its elements? Okay, this is like a heat of formation. This is table I. Okay, so table I we have to go through. We're looking for aluminum oxide, but the key here is that we want 1 mole. Okay, how much energy was released in 1 mole? So let's go to table I. And there it is in all its glory. So table I, and let's go to aluminum oxide. And look, they gave me the heat released. This is in kilojoules. All right, so this is the heat released is, so this is again kilojoules, delta H. So for aluminum oxide, it's negative 3351. But careful, this table is not a great table. Most heats of formation are given per mole. They're giving me the total energy per 2. So this is for 2 moles. They want the energy per 1, so we divide this in half. Okay, 3351 in half, and let's go back to our, and 3351 per 2 moles is the heat for kilojoules. You divide by 2 because there was 2 of them. We want it per 1. Okay, and when you get that, you get your 1676, and that's choice 3. That's simple. Number 43. Number 43, the first thing that I see is I see my energy on my reactant side. That screams to me endothermic. Okay, that means for this to react to make these products, okay? Product side is right here. To make these products, I need for this reactant to absorb this energy, okay? So energy is in the reactant side, the left-hand side. Energy is being absorbed, okay? It's endothermic, okay? Delta H would be positive, okay? But entropy, okay, this is the word we learned that measures, okay, it measures disorder. So entropy is doing what? Well, let's look carefully here. I have 2 liquid molecules with energy become 3 gas molecules. So if I've got 2 particles going to 3 particles, that alone would increase the entropy, right? 2 particles breaking down into 3, you know, so you take something, you break it into smaller pieces and more of them, the disorder, which entropy is measuring, the chaos, is increasing. But even more so, these 2 things are liquids, and we're making gases. Gases have such a higher amount of energy, okay? They're flying around the room hundreds of miles an hour. These guys are so much more random and chaotic than a liquid. So as you go from a solid to a liquid to a gas, your entropy also increases. So energy is absorbed, okay, and the entropy is also increasing. All right, and so that's how that works. Choice 1 is your answer. Number 44. Given the potential energy diagram representing a reversible reaction. Okay, what do they want? Potential energy curves. The activation energy for the reverse reaction. Activation energy is the amount of energy it takes to start a reaction. So I always say, if you want to ride a slide at the park, you gotta get to the top. So the energy it takes to get to the top is the energy to start the reaction, or the energy it needs to get to the point where once you pass this point of no return, the reaction goes, you can ride your slide. So B, okay, is the activation energy of the forward direction. Okay, if there was a reverse reaction, this would be the activation energy of the reverse. A is the potential energy of the reactants, D is the potential energy of the products, and C is the difference where we start and finish. That's your change in energy, or enthalpy, delta H. So we're looking for the activation energy for the reverse reaction. Okay, now of course they don't have a line here for the reverse, right? So if I'm going in the reverse and I want to ride the slide, I got to get to the top. So this is the value I need. But if you look at the chart here, what combination of arrows would give me this one big arrow to go in the reverse? And you guessed it, C plus B would make that value. So B plus C is the answer, choice 2. (45). Which formula represents a molecule of 2-chlorobutane? So in our organic, we learned the first thing is the longest continuous chain. And there's a but there. That's 4 carbons. If you don't know that, you go to table P. And there it is. And this gives me the prefixes for the longest continuous chain of carbons. And we had 4 carbons, or at least I said a but. So that's a 4-carbon chain. Okay? So a 4-carbon chain, well, that gets rid of this guy. That gets rid of this guy. So I'm left with choice 1 and choice 3. Now, 4 carbons is one of the keys. Now, the ane tells me that I have single bonds between them. Now, that would be table Q, but since they're both single bonds, we're not going to go there. Alkanes are single bonded. The next hint is 2-chloro. Now, chloro is a chlorine. Okay, and if you didn't know that, table R would show you that. And there's table R with a chloro. I actually have an example there with 2-chloropropane. There's an example. We have 2-chlorobutane, so you probably could extrapolate there, but a chloro means one of the chloros. Okay? Also, because it is a butane, it's an alkane, it's saturated. Table Q tells you that. Any case, okay, 4 carbons, single bonded. On the second carbon, you have to tell me what's attaching. You have a chlorine group. This is the first carbon. If you count with me, 1, 2, 3, and 4, this is the first carbon it's attached to. Okay, so this is on the second carbon. And of course, we number them so that the carbons have the lowest number possible. So that's why it's 2-chloro and not 3-chloro. 45 is choice 3. Well, it's not choice 3, it's choice 2. Sorry, so this is choice 2. If I was to look at my screen, I would see that this is choice 2. Sorry, so choice 2 is the answer. Number 46. Which formula represents an unsaturated hydrocarbon? We're in organic land. Unsaturated means, okay, that you're not holding on to the maximum number of H's. Let's go to table Q for. Look here. Alkanes. These are saturated. They're holding on to the maximum amount of H's possible. These two are unsaturated. When you have a double or triple bond, because carbon must make 4 bonds only, there are less H's it can hold on to. Look at the general formula. CnH2n plus 2, CnH2n, CnH2n minus 2. We're losing H's as we add double bonds, so these are unsaturated. So we're looking for something that has a double or a triple bond that follows these general formulas. So if I look at these quickly, I look at, hey, CnH2n is one general formula for an alkene. Look at this. There's 2 what? Carbons, so there should be 4 H's. All right, that's why 2 is the answer. Now, if you look at the rest of your choices, they follow the CnH2n plus 2, the alkane formula, right? 1 carbon, double that should be a 2 in there, double that, plus 2 is 4. 3 carbons, double that, 6, add 2 is 8. 4 times 2 is 8, plus 2 is 10. Now, if you don't like that, you could draw them out. Look at C2H4. If you have 2 carbons and you put 2 H's next to that carbon, hydrogen only bonds to carbon as a single bond, and put 1 bond, you see that carbon only makes 3 bonds. You need a second bond, which makes it unsaturated because it can't hold on to more H's. These guys are all saturated. These are alkanes. Choice 2 is your answer. 47. Which ion is most easily reduced? Kind of a strange question, but the only way for us to answer this, since we don't have a net potential table, is to go to table J. So we've got zinc, magnesium, cobalt, and calcium. Now, Table J lists our metals in terms of their activity. Well, solid metals never get reduced. They only get oxidized. So we have a list of metals. Okay? For instance, we have lithium up top, we got gold on the bottom, and as you go up, your ability to oxidize increases, which means your ability to reduce decreases. So the most easily reduced metal is the one that's on the bottom. The best metals love to oxidize as solid metals. And since they're listed as solid metals, you have basically a list of, there's sodium in here and there's lead in here, but this list, as you go up, is talking about their ability to lose electrons. And lose electrons is oxidation. Remember, Leo the lion says grr, losing electrons. So it's a list of how well they lose, which means their ability to get reduced as an ion decreases as you're going up. So what we're looking for is the lowest metal listed on that table. Zinc, magnesium, cobalt, and calcium. Let's go to Table J. Okay, Table J, listing the metals. It does list the nonmetals too, but we're stuck with the metals. So this is the best metal at losing electrons. And our choices, if you remember, are zinc, magnesium, cobalt, and calcium. So here comes my calcium, which looks like of the group the most reactive. Magnesium is the second least at losing electrons. Okay, and then I'm looking for my zinc maybe. Okay, zinc is in third place and cobalt is in fourth place. So of the four metals, cobalt is the worst at losing electrons, which means its ions are able to reduce better. Always put the ones who oxidize above the ones who reduce. So I'm looking for the element that's the lowest here. And of course, cobalt is the answer. 47 is 3, and as you can see, not a great question without net potential table, but you get the idea hopefully there. Okay. Number 48. According to one acid-base theory, they're not naming Bronston and Lowry here, water molecules act as a what? Well, let's see what water's doing. Water in the future is here. I'm sorry, water in the current conditions is water. In the future, okay, it has one more H. How did that happen? Well, that must have happened because HSO4 negative must have given this water a proton. And the Bronston-Lowry theory, they don't name it by name in this Regents, is if you accept a proton because of your lone pair, okay, you are going to act as a base. So water's acting as a base because as you go forward, it has one more H. It accepted a proton. Okay? So it's a base because it accepts a proton. This is the Bronston-Lowry definition of a base. They don't name it, but that's the other. They name Arrhenius, the easiest one, but they do not name this guy by name. So 48 is clearly choice 1. Because it's gaining an H as you go left to right. Now, look with me. HSO4, as it goes left to right, loses an H. This would be the acid. This is the conjugate base. It has one less H. Why? Because it's donating it. Okay? Choice 1. 49. Which one's an oxidation-reduction reaction? Which one is a reaction where electrons are being passed around to create atoms with their charges, their oxidation numbers changing? So you could assign oxidation numbers to all of these, but there's a little bit of an easy way to do that. First of all, I'm going to cross out one that's just horrible. It's a nuclear equation. It's not about electrons at all. It's about the nucleus changing. So nuclear equations have nothing to do with electrons. They're just how the nucleus changes. So these are my 3 choices, and I want to know whose charges are changing. I could assign oxidation numbers here, and I probably will show you, but the answer is clearly going to be 3. And how do you know? Find me a 0, find me an element who stands by itself, whether it's an element like zinc or one of those Hofbrinkels, those diatomic elements. These guys, if you find one 0, you have a redox reaction because it's going from a 0 to something else. The numbers are changing. Look at Sn plus 4 is going to Sn plus 2. Its oxidation numbers are changing because electrons, in this case, are being absorbed by the Sn, the tin plus 4, and zinc is losing them. Okay? If you look at choice 1 and 3, their oxidation numbers stay the same, which means electrons are not being passed around. Acid-base reactions, okay, and Precipitation reactions, double replacements, are not. All of these ions stay the same. Okay? Moving forward. Number 49 is clearly 3. Find me a 0 and you have a redox reaction. Now, there are going to be redox reactions that don't have a 0, and you must be able to assign oxidation numbers. And you just see if the numbers are changing. If they are, electrons are changing hands. And that means someone's losing electrons, oxidation, someone's gaining them, reduction. Number 50, which ends the multiple choice section. Which equation represents natural transmutation? Notice we ended up nuclear, your last unit. These things go in order. Natural transmutation means that an element by itself, because of its instability, whether too many protons, too many neutrons, too less neutrons, okay, gives off a particle and transmutates into a new element. These are nuclear equations. These are not about, guess what, electrons. These are not chemical reactions. So, 3 and 4 are reactions. Okay, this is artificial because you have two atoms that have to be collided together in a particle accelerator, possibly, to create this. Not natural. This is your choice. One nuclide in the reactant side by itself does that, is natural transmutation. Number 50 is choice 2. And this completes the multiple choice section. We have a part 2 coming up shortly.